Hello, my name is Isaac, and today I'm going to present activity number 29, the implementation of a K-means algorithm. But before taking a look into the code, first of all, we're going to explain what is a K-means algorithm. K-means is an unsupervised learning algorithm used to group data into clusters that share similar characteristics. It works in a loop. It assigns each point to the closest centroid, it recalculates the centroid as the average of the points in that group, and repeats until the centroid stops changing much. So now let's take a deeper look into a practical example in Python. So here's the code, and we're going to start from the beginning. First of all, we're going to import the libraries we'll need. It will be numpy that helps with math and arrays, matplotlib that helps create the clustered plots, and makeblobs which quickly generates fake data points with known groups so we can visualize them easily. Now we're going to go to this function. We're going to generate synthetic data. This creates 300 random points around 4 through centers. You can imagine this as customers with similar spending and income patterns. The dataset is two-dimensional, so we can see it in a 2D graph. Now we're going to call the clearing distance function. This function measures the straight line distance between 2 points, for example, between a data point and a centroid. If it's what K-means uses to decide which clusters a point belongs to. Now we're going to take a look into the initialization methods. First of all, we're going to call the random initialization. It just uses k random point from the dataset as a starting centroids. Sometimes it works well, sometimes not, depending on luck. But it's going to be random to have a different points and see how activity and how it changes. Now we're going to initialize with k-means initialization, a smart immersion. It picks the first centroid randomly, then spreads the rest out so they can start far apart. This usually helps the algorithm find better results faster. For the last initialization function, we're going to call the initialize centroids. This function just lets me choose between random or k plus means when I run the algorithm. Here I chose the method k-means++. Now we're going to assign clusters. This function is going to go through each point, calculate the distance to all the centroids, and assigns to the nearest centroid. This is the first step of a k-means iteration. Now we're going to calculate the new centroids with the calculate new centroids function. This is the core of k-means. For each cluster, it takes all the points that belong to it and calculates their average position. That's the new centroid. If a cluster has no points, it just picks a random one to keep the algorithm running. Now we're going to call the plot function. It simply draws the plot function. This simply draws the points in different colors and shows the centroids in a red circle. Now we're going to call the k-means loop. This is the main function. First, it initializes the centroids with k-means++. Then it shows the initial plot, how the points look before learning. Next, it loops, recomputes the centroids, reassigns points, and repeats. And finally, it returns the new centroids in the cluster. Now we're going to use the k-means++ method. We're going to use the k is equal to 5. And here we're going to use the k-means, called the k-means function. And then we're going to plot again, where we're going to plot the change of the centroids that are now given by the new k-means function. So now we're going to run the code with k equals to 5. So as you can see, here are the clusters, 1, 2, 3, 4, 5 clusters, and the centroids are not in the center. And now we're going to see the centroids correctly placed. You can see here I also calculated with 9. So these are the clusters and the centroids, and here are the centroids after the k-means. Conclusions. When I tested the model with the k equals to 5, the results showed well-formed and clearly separated clusters. Each color was compact and the centroid was placed near the middle of each group. Even though the original data had 4 true centers, using 5 clusters only caused a small split in one of them. Overall, the data still looked natural and easy to interpret. The inertia value was low, meaning the clusters were cohesive and well organized. When I tested the k equals to 9, I noticed a big difference. The algorithm created too many small clusters and some of them were extremely close together. The inertia became even smaller, which means tighter groups mathematically, but visually it was clear that we are over-segmenting the data. Instead of finding clear, meaningful groups, it is divided the existing ones into tiny unnecessary subgroups. This made the implementation much less useful. Take a look into my presentation, and I'll see you next time. Thank you for watching.